Okay, so here's all the rules we talked about, right? We've added quite a few tools to our toolkit here for doing derivatives. Makes life a lot easier. What we kind of left off with yesterday was finding some tangent lines. So let's sort of build up to that. What if I want to do something like, for example, let's look at problem 26, how about? Back out. So we're supposed to find the value of the derivative of the function at the indicated point. Okay? And then part 2, I'll show you real quick how to do some tricky stuff on your fancy calculators, where you can do some of the same stuff on your calculators. But for now, we're still not emphasizing the calculators at all. I'm still having you do all this stuff without calculators. So how are we going to do a problem like that one? That does not fit one of our rules at all, right? We don't have I mean, there's a lot of stuff going on. I've got a product of 2 factors there. We don't have any rule for products of things yet. Starting like Friday or Monday we will, but not right now. What could we do to pre-write that before we can do the calculus? Yeah, we got to multiply it out, right? If we distribute the 3x, look what happens. If I distribute the 3x, we get y equals 3x cubed minus 6. Everybody agree? The x's cancel on that second one. Okay, that's easy to differentiate, right? Y prime would be what? What's our general power? Good, we bring the 3 down, so 9x squared. And then what's that one going to be? You were right, you don't even say it, just 0. Right? So we wouldn't even bother with that. The derivative of constant is 0, so that would be our derivative. And so if we want to evaluate that, this is some symbols that we use in math sometimes. If I write an expression like that, I put a vertical line, and at the bottom, I do x equals 2. What does that mean? What do you think? What's that mean?
Evaluating the derivative at x equals 2.
Yeah, the way you'd read that is y prime equals 9x squared at or with x equals 2, right? So if we take this additional part here and we're plugging that in, what do we get? Why don't I worry about the 18? Well, there's no place to plug in a y, is there? Right? In my expression here for the derivative, it's an explicit function of x. It only involves x's. In about 2 weeks-ish, maybe a little less, we'll deal with some examples where we get x's and y's mixed up in our answer. Okay, but we're not there yet. Okay. So what's our answer going to be for this then? Y prime equals, what am I going to get? 36? 36 when x equals 2. Okay, makes sense? What else? Anything else I want to do? I don't think so. I think we're good. We might come back to everything. How would I do problem 28? I don't care about actually doing it, but let's look at a strategy. Raise hands. What do we got here? Suggestions on that? If I want to evaluate the derivative of f of x at that point, how would I take that derivative?
Expand out.
Got to expand it out, right? Expand so simplify. Expand out the expression and distribute the 3, and then I could differentiate term by term, right? Okay? Good. All right, so let's try it. When we go back?
The fourth sign. How do we do that?
Okay, let's do that one. All right, let's do this one.
Okay.
We'll do that one. So I'll save the odd ones. If you want to do those out of the textbook, the answers are in the back. These are kind of good practice. What about this? If we want to evaluate that derivative at the point pi negative 1. Well, we can actually take that derivative directly. What's g prime of t? First term is going to give me 0. Derivative of a constant is 0. So then we get 3 times, I get the derivative of 3 cosine t, but the 3 I can just pull up front, right? If I'm differentiating derivative with respect to t of this term, 3 cosine t, remember that 3, I can just, oh, it's white, it's not true. I can just pull out front, right? So we end up with 3 times, what's the derivative of cosine t? So we get negative 3 sine t. And so if we want to evaluate this at t equals pi, I would just say g prime of pi equals, what am I going to get? Negative 3 times the sine of pi. What's the sine of pi? 0, right? Unit circle,
Oh, side is one.
right, sine's a y component, so that'd be, so we just end up with 0. Personally, I really like the notation where the prime notation, where you have a function with a prime in it, because it's so easy to say, when I want to evaluate a derivative, I just plug that value into my derivative function, right? It's easier to write.
Sine is going to be negative cosine?
That's, okay, so that's the rule, that goes back to here. Derivative of cosine is negative sine.
Oh,
Okay. Okay, so what about this one? Everybody think about this for a second. That looks like a quotient, right? And so we don't have a rule for quotients until the near future, but for now we do not. So we would have to rewrite that to be able to do this one, because we don't have a rule otherwise. What are you gonna do, Kurt? Good, we got a common denominator, so we could just split it up. We could write this as 2x squared over x minus 3x over x plus 1 over x. So first term we just simplify to 2x. Second term, the x's cancel. And then 1 over x, how would I write that as power? There you go, right? Now we're all set up to use our generalized power rule. Some of them you couldn't do. Like, what if on the bottom, what if we had the same kind of thing? What if we had something like 2x squared minus 3x plus 1 over x minus 11? Then we're stuck, right? There's nothing we could do in that one. That's not going to simplify to a point where we could do that derivative now. Right. Some of them we could. Would this one work? That would, right? That's going to factor, that one would factor out to where if I actually divided this out, I'm going to end up getting, yeah, I'm going to get, so that's x cubed minus 3 cubed, right? So what's our, and you know, gosh, I got to find time to do this. I got to find a convenient time for you guys to, but we got to do a little memorization quiz over some things so you get a few things down that just don't seem like they're right at the top of your head. What if I have x cubed minus a cubed? What's that factoring pattern?
X squared. X
Plus.
plus 2x.
Right? Okay. And you may not remember that totally, but that's it. So this one would factor into, you will, I promise you will remember. So that's going to be x squared plus 3x plus 9 over x minus 3. So those cancel, and so that actually does simplify to that function, right? Does that make sense? So if I wanted to evaluate this, well, you know, that's a terrible example, kind of, isn't it? Well, no, it's not. If I wanted to evaluate this at, what if I wanted to evaluate the derivative, never mind, I could do this. What if I want to evaluate the derivative at 7? It's a great example. Never mind, I don't know what I was thinking. So now I get f of x in a form that I could differentiate. Right? Everybody see that? So now I could say, if that's f of x, f prime of x is now equal to what? What's the derivative of that expression? 2x plus 3, okay? Okay, one thing I would have to do though, and this doesn't get talked about a lot in math, but it's important to remember, are there any values of f of x, or any values of x for which that function is not defined? 3, right? So if we rewrite it like this, I still have to include the fact that x cannot equal 3, right? So in our derivative function, that's also true. X cannot equal 3. We couldn't, for example, try to evaluate this derivative at 3. How come? Because the function doesn't exist at 3. That's kind of some fine print. It's a subtle point, but you get that? What did we do? This goes back to chapter 1. When I rewrite this function, this rational function, as x squared plus 3x plus 9, think what I've done. I've taken a function that had what kind of a feature at 3? A whole, because it's a 0 over 0, right? At a value of x where I have a 0 at the top and the bottom, that's a whole. If it's a value of x where the bottom is 0 but the top is not, what is that? Vertical asymptote, right? If I get a number over 0, that's always a vertical asymptote. But we took a function that had a hole at 3, and we created a new function that just filled in the hole, right? Everybody get that? Okay. But we can do that because it makes it an easier function to graph, for example, but we still have to remember that x can't equal 3 because that's a 0 in the denominator. Okay? All right, questions on that? Okay? How about something like this? Finding tangent lines. So let's do, this is kind of what we left off with yesterday. We did one example. Let's do, how about, let's do 45. Yeah, that's good. So if I want to come up with the equation of a tangent to this curve at that point, what do I need to write the equation of a line? What's the recipe? Slope and a point. That's it. Right? Slope and a point gives me a line. So where is my slope going to come from? Whose job is it in calculus to give me the slope? Well, we're going to need that to write the tangent line. What does this function do? F of x equals 1 over the cube root of x squared. Well, the function, I input stuff, and what does it give me back? Like if I input 20, what's f of 20 mean? The y value. It gives me the value of the function for a given x value. So it tells me where on the curve, what the y value is. That's the job of the function, right? It outputs functional values or y values when I input an input value, right? What's the job of the derivative? If I input, so f prime of 20 would mean what? Slope of the curve at 20, right? So it's the job of a derivative function to give me slopes when I give it input values. That's its purpose, right? So this is giving me, I already have the point. If I plug in 8, I get back 1 over 4. They already did the work for me. There's the point of tangency. But I need to know the slope at that point. So I got to use a derivative, right? That's the job of the derivative. So I have to take the derivative first, come up with the derivative function before I can evaluate it at 8. What do I have to do to this, though, to put it in a form where I can differentiate it?
Write it in terms of power.
Gotta write it as a power. So what's that going to be? The fact that it's on the bottom, what's that tell you about the exponent? Negative. So I'm going to get x to negative something. Well, how would I say the cube root of x squared? 2/3, right? The index of the radical goes on the bottom, the exponent goes on top, right? So we get negative 2/3, and so then what is f prime going to be? I just follow my rule, right? Whatever the exponent is, that goes out front. 5/3. Negative 2/3 minus 1 minus 3/3 is negative 5/3. So there's my derivative function. The slope of the tangent line is just equal to f prime of 8, right? So I get negative 2/3 times 8 to the negative 5/3. Well, what's that going to be? So I get a negative 2 on top, a 3 on the bottom. I get an 8 to the 5/3 on the bottom. How do we do that? When I do an 8 to the 5/3, we can do that in our heads. What are the two steps? What do I do first? Cube root. So the 1/3 power means a cube root. So cube root of 8 is 2 to the 5th. (32). So on the bottom, I'm going to get a 32. So negative 2 over 3 times 32. That's going to reduce to a negative 1 over 16. So I get negative 1/48, right, is my slope. That's the slope of the tangent line. I already have the point. They probably ask for this in, well, they don't ask for any form. So what's the easiest way to write that from yesterday? What's it called? Point slope, right? We'll just write it in the form y minus y1 equals m times x minus x1. So y minus 1/4 equals negative 1/48 times x minus 8. Right? So if I wanted to solve for y, all I'd have to do is just distribute the negative 1/48 and add 1/4, and I can put it in the slope intercept pretty easily. Right? That should be fine. Okay, make sense? Okay? They might expect you, yes, sir. Oh, okay, yeah, I think I was about to, yeah. So they might ask for it in slope intercept form, possibly. So if they do, then that's unfortunate. What would you have to do with this? I mean, what I just said, you'd have to distribute the negative 1/48. So I get negative 1/48 x. Negative times negative is positive. 8 over 48 just reduces to 1 over 6, right? And then if I add 1/4 to both sides, negative 1/48 x plus 1/6 plus 1/4, what's that? I can get 12, so I can get 2 plus 3 over, so 5/12, is that right? So I get y equals negative 1/48 x plus 5/12. Okay? So I know on the AP test you can leave it like that. I wish it was that way, but in Math Excel, I don't have a ton of control over how they want the answer. I'd say just try it once and see. I don't know the answer to that. Yeah. Hopefully they'll take it that way. Okay, so next issue. So summarize, what have we done? So we've kind of built up to the point now where we can use the derivative function to calculate a slope at a point so we can actually build a tangent to a curve. Oh, how are we going to do this on the calculator? Oh, let me show you. Use the derivative function, okay, from your results. Okay, so have a look here.
Mine's dead also. What? Oh my gosh, another one done. I know, I just what I got.
Yeah, well, you don't want to, if you put the two numbers wrong there.
No, it's like if you hear.
Okay, so what could we do here? So on here's a couple ways you can do this on your calculator. So if we take this function, y equals
I'll use my fancy little fraction template. How about I get 1 over. Now it'd be easier to just write that as x to the 2/3. There is a way, I believe, if I go to let's try. No, not on those.
Yeah.
You see it?
6.
Oh, there it is. Maybe 6, yeah. So I get, yeah, there we go. We get the cube root of x squared, okay? Would have been easier just to write that as 1 over x to the 2/3 or x to the negative 2/3. Let's graph this function. Now we want an x value of 8. So we might as well choose our window to be nothing crazy. Let's set our window to go from, how about 0 to 10? If I set the x's to go from 0 to 10, how do I let the calculator choose the y's? Do you remember from Algebra 2? Zoom fit. So zoom 0. You have to go down, just zoom and then type a 0 is fine. So now it gives us the function, right? Graphs it between 0 and 10. So if we want to know at 8, and it looks like that's way overkill, let's change our window a little bit. We don't like it. Instead of going from, let's have it go from 0 to like 1. That looks a little better, right? So a couple things we can do then. And this, some of this ought to look real, sound real familiar. Did you guys use your calculators a bunch last year? Not a ton. So one thing you can do, if we want to know what the value of the function is, pretend we didn't know the 1/4 part. Okay, we could go trace 8, enter, and look what it does. Tells us the value of the function there. So there's the point of tangency. Okay. If I want to know what the slope of the curve is there, I go to my bag of tricks. I go second calc, so second F4, and which of those options now makes sense as the one that's going to give you back a slope? dy dx. So we type in 6, we type in the value of the function, so we enter an 8 and hit enter, and what does it tell us? Well, there it is. There's the slope to, quite a few decimal places. Unfortunately, there's no way to store that, so you have to kind of write it down. But if I wanted to come up with the tangent line then, all I would have to do is use that slope and the point of tangency to create the tangent line. Okay? What's kind of nice about Desmos, while we're on the subject, let's use Desmos here real quick. You can't use Desmos on the AP test, but there's more to life than the AP test. So if we graph the function f of x equals, what was it, 1 over x to the 2/3? So let's do x to the negative thirds. There it is. Okay, we'll just kind of focus in over here, how about, in this part. So on Desmos, if I want to do a derivative function, all I got to do is this. I can say something like g of x equals f prime of x, and it gives me the derivative function right there. That's really cool. So if I want to know the slope of the curve at 8, all I've got to do is evaluate g of 8, and there it is. How cool is that? So now I've got the value of the derivative there. If I want to come up with the actual equation of the tangent line, the beautiful thing about Desmos is you don't have to solve for y. So we could put this in point slope form, right? So we could do y minus the y value. What if I don't know the y value? I could do y minus f of 8. I don't even have to put in the value. I can let it calculate it for me. How cool is that? Equals the slope, which is g of 8, or I could even say f prime of 8 times the quantity x minus 8. How cool is that? That's giving us, if I zoom out, you can clearly see that is the tangent line at that point. There it is. That's pretty amazing. See what a powerful tool that is. Desmos is, it's great. Okay? To do what now? Yeah, well, yeah, there is a, is that what you think about that calculator?
I didn't need to.
Yeah. So there is a version of the TI called the TI-89, which is a computer algebra system, which essentially does this stuff. It's a little more cumbersome to use. Yeah. Well, yeah, it's called an iPhone.
Well, okay, but like if it was like that's all it did. You just
Most tests probably won't let you carry that in there.
No, they won't. And they won't let you use a TI-89 either. So you're kind of stuck with an 84 on the AP test, But once again, that's just a test. I mean, if you were actually doing calculus, like if you're an engineer and you're doing calculus, what would you do? Well,
An 89 or Desmos.
I would use Desmos. Yeah.
And I would love to see you come in.
I would.
I think it's
She'd
good.
call us joy every single day.
I need a little bit of that paycheck then.
The engineering life is not the life of me.
That just reminded me of something funny.
I know what you're thinking about. Funny video of my brother.
Yeah.
Oh,
We'll bring it sometime. We gotta find out.
that was so funny.
Yeah. Okay, so let's go ahead and do 52. And that probably brings us to a close for today, I bet.
I was doing before this.
Have you guys hit that point today?
No, it was like after
I had
the
weeks
your
ago.
head's just kind of like.
Okay, that's true though. That's a good thing. But what you must do in those situations, which is what's horrible with our schedule, what's great about college is that's how you work your brain. You work really hard until it's tired, and then you go unwind. Take a break.
Bro, I
There
cannot,
you go.
I have to go home and study for tests that I should have been done with 2 weeks ago.
So what about something like this? How much time we got? Like 7 minutes?
Both of them.
Oh.
12 minutes. Okay, we got time. Let's do one more of these. So here's the other issue that's going to come up on assignment 2 and assignment 3 for this section. So determining the points, if any, at which the function has a horizontal tangent line. That must sound like a bizarre, contrived problem to do, but this is one of the holy grails of calculus. We're going to start, in the near future, we're going to specifically go hunting for these places with curves. And in the real world, that's what we do a lot of times. We're trying to find the points at where the places on a function where it has horizontal tangents. And it might be some kind of a profit function for a corporation, or it might be, there's real world applications where that's something we always want to find. What's unique about a horizontal tangent line? What's the value of the derivative? No, it does exist. It's 0. Yeah, it's equal to 0, right. Vertical tangent line wouldn't exist, right? But a horizontal, it's equal to 0. So we just want to, this is a pretty easy thing to do algebraically, conceptually. We're just going to take the derivative and then set that function equal to 0, right? We're going to ask the question, ask the math gods, when is the derivative equal to 0 by solving that equation, right? So let's do 52. So what is y prime here? So I've got the square root of 3 times x. That looks complicated, but what's the derivative of the square root of 3 times x? Square root of 3, right? Because the derivative of x is just 1, right? So we took the square root of 3 out in front, and we took the derivative of x. Same thing here. We'll take the 2 out in front of the derivative. What's the derivative of cosine x? Negative sine x times 2 is minus 2 sine x. Okay? So horizontal tangents are going to occur, you told me, when y prime equals 0, right? So here's how I would communicate this then. We would say y prime equals 0 when that equals 0, right? So the square root of 3 minus 2 sine x
equals 0, and all we're doing then is solving for x, right? This is our petition to the math gods for the places where that's true, and now we got to do the work to find out where they are, and that's how they communicate with us. They're kind of ornery that way. They don't want to give you the answer easily. So what do we do to solve for x here? This is a good, I picked this one on purpose because it's a trig equation. So you got to kind of think about incrementally solving a trig equation, right? Getting to that x is a little bit of a problem. Well, it's not a problem, but it's a multi-step process. First thing you have to do is just isolate the trig function that it's embedded in, right? So first step is to isolate sine x. So we could push that term to the other side. So then sine x, if we just flip sides, sine x equals 2 over the square root of 3. Did I square root of 3 over 2? What did I just do? I was saying that's not right. Square root of 3 over 2. Okay, and where is that true? Well, that's a unit circle question, isn't it? Right? Now we say sine x equals square root of 3 over 2 when x equals what? Square root of 3 over 2 is going to be the coordinate there and there, right? Everybody agree? So those are going to be the two locations. This one has coordinates 1/2 square root of 3 over 2, and this one has coordinates negative 1/2 square root of 3 over 2. And there's some reflected points down here, but those have negative y values. Okay, fortunately, we're bailed out a little bit. We're restricting the domain on this to one lap of the unit circle, right? So from 0 around to 2 pi. So there actually are only two locations. If we didn't restrict it to one lap, there would be an infinite number of times we hit that spot and that spot, right? So what are those values then? What are the angles that go with those? This one is at pi over 3, and this one is at 2. Right, so those would be our two answers, right? We're either getting x equals pi thirds or x equals 2/3 pi. Okay, make sense? Okay, what if we asked, skip that. What if we asked instead, could I have asked a similar question? What if I had said something like, find the points, if any, at which the function has at which the tangent line has a slope of 1. What would I have done differently in the equation? Yeah, instead of setting the derivative equal to 0, I just would have set it equal to 1 and solved a different equation. Right? Does that make sense? And then the values of x that are solutions of that equation would be the places where that happened. Okay? All right. I think this is going to be I don't really want to jump into that. Okay, we're about to get into a bunch of really good physics. I'm going to save that for tomorrow. I don't want to pile too much on. I think that's good. So tomorrow, I love tomorrow. Today we get to talk a little physics in here.